Hi everyone, I'm Yang Liu, and today I'm going to be presenting on sparsifying generalized linear models. This is joint work with Arun Jampalapati, James Lee, and Aaron Sidford. To start, let me introduce the problem of sparsification more broadly. In the sparsification problem, we're given functions f1 through fm, and think of these functions as being from Rn to R, where m is larger than n normally. And consider the sum function f defined by f of x equals the sum of fi of x from I equals 1 to m. We say that f tilde is an epsilon approximation to the sum f if their difference is at most epsilon times f. In other words, it's a 1 plus or minus multiplicative approximation everywhere. Additionally, we would like that this approximation f tilde is sparse. So formally, we say that f tilde is as sparse with respect to f if f tilde can be written as a non-negative linear combination of f1 through fm for some non-negative weights, where the number of non-zero weights is at most s. In a lot of sparsification problems, it would be great to achieve a bound of the form n over epsilon squared times polylog of n for the sparsity s. And throughout this talk, you can think of this as being the sparsification procedure being successful. A natural application of sparsification is to the least squares regression problem. In this problem, we have vectors a1 through am in Rn and b1 through bm. Once again here, think of m being larger than n. And the goal is to find x such that ai.x is approximately bi for all I. When the loss is in the L2 norm, this is exactly minimizing ax minus b 2 norm squared, where a is the matrix whose rows are ai, and b is the column vector with entries bi. To cast it in the language of sparsification, you can think of the ith function fi as just being the loss squared, so ai.x minus bi squared. And thus the total sum loss is capital F of x being ax minus b in the L2 norm squared. Imagine that we've computed a sparsifier s for f of x. And here s is just denoting the non-zero coefficients that we use to get the sparsifier. Then, if we wanted to solve this L2 loss problem approximately, we could just instead solve it, the sparse L2 loss problem, f tilde, and this would provide an epsilon approximation. So sparsification is one way to reduce the problem size possibly significantly while still maintaining a good approximation to the value of optimization problems. Beyond regression, there's been application of sparsification to graph problems. In graph sparsification, in general, we are given a weighted undirected graph G, and our goal is to find a graph G tilde with a subset of edges that has not too many edges itself, and that approximates various objectives. In the cut sparsifier problem introduced by Benser and Karger, these functions f that we wish to sparsify the sum of are just weighted absolute values of differences across edges. In other words, the total function f of x is the sum of wuv times xu minus xv. In the spectral sparsifier problem, we're given that the function f is w times the difference of xu minus xv squared. So as you can see, these both fall in the setting of sparsification because they're the sum of kind of single functions. In this case, even apply to linear objectives. In this talk, we'll be studying the problem of generalized linear models, which actually extend both examples discussed on the previous page. In this problem, we have once again f of x being the sum of functions, but here we should think that the sum of functions are functions of some linear form of x. So phi of ai.x minus bi. For different functions phi, a lot is known about sparsification. For example, when phis are just power functions, so phi of y is y squared, it's known that you can achieve s at most n over epsilon squared, and this is in fact tight. For other values of p other than 2, in particular p less than 2, it's known that you can get n polylog n over epsilon squared. And for p greater than 2, it's known that something like n to the p over 2 over epsilon squared is tight up to polylog factors. More recently, for motivations that I'll discuss a little bit later, it was asked whether you can sparsify functions that go beyond these power functions discussed on the previous slide. For example, a natural function is the Huber loss, which for the purpose of this talk, you can think of as being an approximation to the min of the absolute value and the square, or more generally, what I'll call the gamma p functions, which are the min of a p power and the square. For these settings, it was recently shown that you can achieve sparsity in most n to the 1.17 over epsilon squared, but a tight bound of n over epsilon squared was not known. Additionally, there's some functions like the Tukey loss, which are min of 1 y squared, which also some sparsification results are known, but are a little less smooth than the Huber and gamma losses that are mentioned above. While we've seen a lot of positive results for sparsification, I did want to mention for intuition a function that does not admit sparsifiers. For example, here, this is basically some kind of shifted ReLU function. It's like 0, and then it goes positive, and then it goes negative again. So this ReLU function, you can show, requires exponential size sparsification. And the intuition for constructing it, while I won't go into too much detail, is to take a set of points on the unit sphere whose absolute value with each other is large, like greater than 0.1 or 0.2. Then you can use these to these vectors AI will construct a family of functions for which phi of y does not admit sparsifiers. And it's known that you can find exponentially many points on the unit sphere whose inner products are all large. The motivation for us studying this problem partially comes from applications to LP regression for p less than 2. More concretely, this problem is to minimize ax minus b p norm, where p is between 1 and 2. This is a convex optimization problem. While if you care about providing a 1 plus or minus epsilon approximation, it suffices to just sparsify the LP norm. However, it was actually shown by Gadiri, Penn, and Bempala that if you wanted high accuracy LP regression, in other words, logarithmic dependence on the error parameter epsilon, this can be reduced to efficiently sparsifying sums of gamma p functions. And this motivated us to study the more general question of sparsifying generalized linear models. To say a couple words about how the proof works, it uses iterative refinement and the fact that the Bregman divergence of the p power function is actually this gamma p function up to constants. By combining these, Gadiri, Penn, and Bempala basically showed that high accuracy LP regression can be reduced to sparsifying sums of gamma p functions. So given this, it's time to state our main result. Our main result is that if h1 to hm are functions from R to R plus satisfying the following. The first condition I'm going to call auto-Lipschitzness. The difference of H2 and HV is the most HI U minus V up to constants. And the second is some kind of non-degeneracy condition. It just says that the function is growing slowly, at least lambda to the theta for some strictly positive constant theta, and for all lambda, at least 1. Then under these conditions, if we define the functions fi to be hi squared, and for any vectors a1 through am, the sum function f of x is sum of hi ai dot x squared. This admits an S-sparse sparsifier, that's 1 plus or minus multiplicatively approximate, when the values between alpha and beta. And the sparsity is in most basically what you would expect, n over epsilon squared times polylog n, and then there's an extra logarithmic factor in beta over alpha. Additionally, we can compute this sparsifier very efficiently, basically in the same time as it takes to find the leverage scores of a matrix, which are used for L2 sparsification. Our framework, these hypotheses above, apply for the functions h squared is u to the pi, so basically p's power functions when p is at most 2, and also when these hi squared functions are exactly the gamma functions mentioned earlier. So we achieve sparsifying gamma functions. And thus, we get a high accuracy algorithm for LP regression when p is between 1 and 2, and it runs in time n and za plus n to the omega, which is nearly optimal for the current value of omega. I wanted to give a little bit of intuition on these conditions that we have in the theorem for sparsification. So remember that the conditions are auto-Lipschitzness and lower growth, as we call it. So you can actually use these two conditions, in particular auto-Lipschitzness, to prove that another condition holds, which is approximate symmetry, which is nice. And also, the first condition, again, can be used to show that the function is growing at most linearly. So h of lambda u is at most lambda hu for lambda greater than 1. And f of lambda u is at most lambda squared f of u when we go back to the functions fi, because fi is h squared. So 4 says that f grows quadratically. And note that this is essential for sparsification because as mentioned earlier, it's known that if p is greater than 2, the pth power function requires size at least n to the p over 2 over epsilon squared to have sparsification. I also wanted to mention that even though condition 2 does not hold for the Tukey loss mentioned earlier, f equals min of 1 and z squared, we are able to still obtain some sparsification results for it with the following trick. You can smooth the Tukey loss f to the following loss function, min of z to the delta z squared, where delta is some very small constant. So basically, we smooth the Tukey loss to a gamma function for very small constants delta, and then we take delta to 0, we trade off, and somehow this eventually gets s at most n to the 1 plus little o1 over epsilon. So condition 2 is, in the end, not so important. Really, the auto-Lipschitzness is the condition that really makes sparsification possible in some sense. Previous work of Musko, Woodruff, and Yasuda had very similar conditions for their sparsification results. To say a little bit of the differences, in that paper, condition 1 auto-Lipschitzness is replaced by what they call subadditivity. So note, which is h of v plus w and most h of v plus h of w. Note the one's a little bit weaker because we can take w to be u minus v, and you can deduce subadditivity from auto-Lipschitz, you can deduce auto-Lipschitzness from subadditivity. So our theorem is a little bit stronger. We have weaker hypotheses that we need to establish our theorem. Another possibly more interesting difference is that in the work MMWY, it requires that all the functions f1 through fm are the same for their analysis to work. Our analysis does not require this at all. The functions can be arbitrary and our proofs still go through all the same. At this point, I'm going to go a little bit into the ideas behind our sparsification result. As with all sparsification, our algorithm is based on importance sampling. In importance sampling, given the functions f1 through fm and their sum, the goal is to find a probability distribution over the m functions f1 through fm, such that if you were to sample indices from the probability distribution row, and then take a unbiased average of these samples to hope that it's a sparsifier. So put a little more concretely, you can show that for this choice of f tilde, it's 1 over s times sum of f of the index divided by the probability of the index, that this sum is in fact unbiased. The expectation is exactly f of x. However, to have sparsification, we need to establish that the difference is at most epsilon times the function value for all x. This seems to present a little bit of a challenge initially because there's exponentially many points x in Rn, even if you were to take an epsilon net. So towards this, let's just consider the following statement. Let's think how to find weights such that for such that for any fixed value of x, we're able to achieve that fx minus f tilde x is the most epsilon times lambda with high probability, where lambda is like the value of fx approximately. And then I'll say a few words about how to union bound over all points in Rn. To construct these sampling probabilities, the main challenge is the non-homogeneity of Fi. This is because when the Fi are homogeneous, there's a known sampling probability called the Lewis weight that works very well. Now, because our function is non-homogeneous, we're not able to use Lewis weights. So our idea to start is to fix a kind of scale for the functions. And intuitively, this scale is needed to handle function values between lambda over 2 and lambda. Though this is not actually completely true, because even if we wanted to sparsify at a single level of scale, we still need weights at log m levels. So this is really just intuition, but the analysis works quite a bit differently. Given this level of scale lambda, we can define importance weights just at the scale lambda, and they satisfy the following formula. For all I from 1 to m, if I was to take fi of square root of ai transpose m inverse ai divided by di times ai transpose m inverse ai, where m is the matrix di ai transpose for some positive weights di. So then we call the matrix M approximate weights for the level lambda. Given this approximate weight matrix M, we can find the leverage scores of the matrix M, which are given by di ai transpose M inverse ai over n, and this will give our sampling probabilities just at the level lambda. Now, to build the overall sampling algorithm, we're going to repeat this for all lambda equals powers of 2. For lambda between our desired range alpha and beta, but you have to divide by extra poly n factors to get it to work. So that's the overall algorithm. We find some matrix M that represents approximate weights, and then we sample by the leverage scores of the matrix M. That's just at the level lambda, and then we go over multiple levels of lambda to find our actual sparsifier. It's even unclear why these weights exist. So to explain why the weights exist, we use an idea of Cohen and Penn, which is a contractive map. If you define psi of D, remember D is the diagonal weights of the matrix M, to be 1 over lambda times f of this square root function over ai transpose m inverse ai, well, what you can show is that an approximate weight is an approximate fixed point of the map psi. So if you were to apply the map psi over and over and over, then you're going to get eventually converge to an approximate weight in our state. Once again, just to explain, psi is exactly defined so that psi d approximately d is equivalent to d being an approximate weight. So we just need to argue that psi is a contractive map, and we do that. And because it's contractive, we are ultimately able to prove that if you just start at any point and keep applying psi over and over and over, that eventually you converge to an approximate, the optimal approximate weight. Of course, now that we have these weights, we still need to argue that if you sample by these weights, that you actually construct a sparsifier. So you want to show that fx minus f tilde x is the most epsilon lambda with high probability for a random sample given by these approximate weights. Now, to say just one sentence about how this is done, the proof is quite complicated, but we use a chaining method, which is an efficient way to union bound over all Rn. This is a method, the generic chaining method was an idea fleshed out by Talleyrand. So the high level idea behind a chaining proof is first, you want to establish that for these weights that we've chosen, that for any fixed x, that when you sample by these weights, that fx is approximately f tilde x with high probability. Of course, there's now exponentially many points in Rn, even with an epsilon it, so you can't just naively union bound. The idea is that you can prove that the number of points x where the variance of the sample is large is kind of small. So then for these points with large variance, where this estimator has large variance, you just union bound over them. And then you go to the next one level higher variance scale, and you bound the number of points with that variance. And you go to the next level, etc. And this gives you a way to union bound over all of Rn. This part of the proof critically uses the auto-Lipschitzness condition. Okay, to summarize, in this talk, we talked about sparsifying functions f of x, which were the sum of fi ai.x, which we termed generalized linear models. We obtain near linear size sparsification under natural assumptions on fi, auto-Lipschitzness, and lower growth. The main parts of the proof were to define approximate weights at each level of scale for the function because the functions are non-homogeneous. These weights are proven to exist via a contractive algorithm. And then we analyze the sparsification by sampling by these weights via chaining methods. As for some future directions, our proof currently does not work for p greater than 2. So note that condition 1 is currently HIU minus HIV, most HIU minus V, auto-Lipschitzness, and we treat the functions to be h squared. Well, I think a natural conjecture would be that if fi was hi to the power p, where p is greater than 2, then you obtain sparsifiers of size n to the p over 2 over epsilon squared. Though we're currently not able to establish that for technical reasons. Additionally, this is for exactly one-dimensional sums of functions. So what if the functions are not functions of like some one-dimensional inner product? What if the functions are fi of ai times x, where ai is a d by n matrix? What properties would we need on these functions to have sparsification? A natural goal would be something like dn over epsilon squared, though I currently don't actually see why n over epsilon squared is not achievable. A lower bound might be quite interesting. Now, it also would be interesting to find other applications of our sparsification result to other problems. For example, beyond like norm-like problems, like the thing we're studying here. What about corsets or other more geometric settings? So that's all I had. Thanks.